This is section 2.7b, nonlinear inequalities. Inequalities involving rational functions have critical points at zeros and asymptotes. All right, so in the last section we did some nonlinear inequalities, quadratic inequalities, and we solved those in two ways. One was using disjunctions, and the other way was just using test regions and finding out what the sign was for particular x values in those regions. And that second method is what we're going to use for inequalities involving rational functions. Now, all they mean by critical points are, those are points at which the sign can change. It doesn't necessarily change at a critical point, but if a sign change happens, it happens at a critical point. And that's why those points are going to be important when we're solving these inequalities. Here's an example of an inequality involving a rational function. X plus 2 over x squared plus 2x minus 3 is less than 0. And so if we want to solve this, we're going to use the second method that we used in the last section, which is the method of test regions. And so let me walk you through this example, and then on the next screen you're going to be able to try and do one on your own. So the first thing we do is we factor the denominator. And we do that because we have to see if there are any vertical asymptotes. And as you remember from earlier in this chapter, vertical asymptotes will be x values that would yield a 0 in the denominator. And this particular rational function does have two vertical asymptotes. It also has a 0, so we find that by setting the numerator equal to 0, solving for x, and we find out that negative 2 is a 0 of this rational function. And now to find the asymptotes, we simply set that denominator equal to 0 and figure out which x values will make that statement true. And it turns out that the values 1 and negative 3 will. And therefore, 1 and negative 3 are asymptotes, vertical asymptotes. All right, so now we have our critical numbers, and we have three critical numbers in this case. We have negative 2 because that's a 0, and we have 1 and negative 3 because those are asymptotes. So we draw our number line and do our test regions, and we find out what regions will give me positive values for the function and what regions will give me negative. Now, you can pick any point in these regions, and once you find out what the sign is of the function value that x-coordinate yields, then you know what the sign is of any function value in that x-coordinate interval. You know it. You know what it is. Because sign changes can only happen at zeros, or in the case of rational functions, at vertical asymptotes. All right, so in this region over here to the left, let's say we chose to test x equals negative 4. Well, plugging negative 4 in for x, we would get negative 4 plus 2, and that's negative 2, over negative 4 minus 1 is negative 5, negative 4 plus 3 is negative 1, and so that would be positive 5, and that would just end up being negative 2/5. All right, so we know that negative 4 plugged in for x will yield a negative function value, and therefore everything in that region is negative. Let's suppose we test something in this region here. Well, we could test negative 2.5, and if I plug negative 2.5 in for x and do the arithmetic, I can clearly see that I'll end up with a positive number. The same is true if I plug in something from this region. Easiest number in this region here is 0, and if you plug 0 in, then you're going to end up with a negative number, and therefore everything in the region is negative. And finally, if you plug in anything from this region, easiest number would be 2. Plug 2 in for x. Then you'll clearly see that everything's positive, and therefore I know which regions will give me positive function values and which regions will give me negative function values. Now, since this original inequality is x plus 2 over x squared plus 2x minus 3 is less than 0, then the regions that I'm interested in are the negative regions, because that's less than 0. And this is what the solution set would look like. I'm going to have parentheses, and the reason I have parentheses is because since it's less than 0, it does not include the values, that is, the endpoints of the intervals. It does not include the values that would yield 0. Okay, now that's the reason why there's a parentheses at -2 here, because the endpoint is not included. Since -2 will give me an overall function value of 0, that 0 is not less than 0, and therefore it's not included. Now, you might ask, well, why is there a parentheses at -3, one of the vertical asymptotes, and why is there a parentheses at 1, the other vertical asymptote? And the answer is simply that 1 and -3 are not in the domain, and therefore they cannot be included in the solution set. And so we would write in interval notation this solution set as parentheses negative infinity, comma, -3, union, parentheses -2, comma, 1. All right, here's an example. This is something that I want you to do on your own. I will give you a little hint first, and that simple little hint is you want to get 0 on one side, because see, when you have an inequality and zeros on one side, the reason that makes it easy is because then it puts everything in terms of positive and negative. Something's either less than or equal to 0, or it's greater than or equal to 0, which means you're dealing with positives or negatives. That's going to make things a lot easier. So your first step is going to be to try to get 0 on one side, and then you're gonna work with that key. The key to the strategy is find a common denominator, and just do this on your own. Pause the video, do it on your own, and then resume if you get stuck. Now, if you do get stuck, what you should do is only resume until you get unstuck, and then try to do the rest on your own. But basically following the strategy of what we saw on the last screen, you should be able to do this problem on your own. All right, going through the solution, we first move the 3 to the left side so that we get 0 on the right side. Then I need to find a common denominator, that's x minus 5. And so this is how I will get everything over one denominator. Now, you've done this before. You did it in grade school math, so this is nothing new. But it's amazing how sometimes simple things like fractions and common denominators and arithmetic steps we can get rusty on those. So let's just take a tiny second to examine this. See, x minus 5 or x minus 5 is basically just a fancy way of writing 1, the number 1. And anything times 1 is itself. And so we really haven't changed this inequality at all by putting x minus 5 over x minus 5 here, because that ratio is simply 1. And it'd be the same, for example, of simply writing this inequality that I'm circling now with a mouse arrow, of writing that inequality as 2x minus 7 over x minus 5 minus 3 times 1 is less than or equal to 0. It's the same thing. All right, so we have our common denominator. Now we're going to combine them. And when we put them together, we've distributed a 3 here. This 3, we can consider it a -3. And so negative 3x, negative 3 times negative 5 is plus 15. So 2x minus 7 minus 3x plus 15 over x minus 5. Now we can combine like terms further, and this is what we end up with. Negative x plus 8 over x minus 5 is less than or equal to 0. Continuing now with our method, we divide the number line into intervals using our critical numbers as endpoints. Why are 5 and 8 critical numbers? Well, 5 would give us a vertical asymptote because 5 would yield a 0 in the denominator. And 8 is a 0 because 8 would yield a function value of 0. So those are our critical numbers. And then we do our test regions. And we find out that we have negative in the left region, positive in the middle region, and negative in the right region. And again, just to repeat something because it doesn't hurt to keep saying things. Every time you hear it, you learn it a little better. When you test any value in this region and find out what the sign is of the resulting function value, every function value in that region will have the same sign. Okay, so now that we have our intervals and we know where the positives and negatives are, we can first graph our answer and then write it. Graphing the answer would look like this. Since I'm interested in the negative region, since this inequality is less than or equal to 0, I have this negative region here. Why do I have a parentheses? Because 5 is a vertical asymptote, and therefore the number 5 is not in the domain of this rational function. And then on the right region, I also have negative. And the reason I have a bracket is because 8 is a 0. And if the function value is 0, it still satisfies this inequality because the inequality is less than or equal to 0. That's why the bracket is there. And finally, translating the number line graph into interval notation, we have a solution set of parentheses negative infinity, comma 5, union, bracket 8, comma, positive infinity. Here's a word problem that uses inequalities. This particular one doesn't involve a rational inequality. It's just a simple inequality like what we did in the last section. And so here is how it works. We have one leg of a right triangle. It's 2 inches longer than the other. How long should the shorter leg be so that the area of the triangle is greater than or equal to 4? All right. The first thing really is to draw, and so I'm going to just draw that for you. This is what it looks like. This is what the problem is asking. This is how it looks with the diagram. X is a shorter leg, x plus 2 is the other leg. And we know that the area must be greater than or equal to 4. Okay, so at this point, you should be able to figure this out. Express the area as a function of x. You can do that. And then set up an inequality. And then solve that inequality with the method of intervals and positive negative regions. Pause the video, do that, and then resume when you have an answer. So the area of a triangle is 1/2 base times height. We know that from geometry, and I'm sure you already have that formula etched in your brain. And then solve 1/2 times x plus 2 times x because it's just we can consider x plus 2 our base and x our height. We know that that area must be greater than or equal to 4. Now we simplify. X plus 2 times x is greater than or equal to 8. We simply multiply both sides by 2. Then we bring the 8 over because we want to have 0 on the other side. And now x squared plus 2x minus 8 is something we can factor as x plus 4 times x minus 2. And now we have our critical numbers because our critical numbers, since this isn't a rational function, our critical numbers are only going to be our zeros. Our zeros are negative 4 and 2. So x equals negative 4, x equals 2, those are our critical numbers. And then when we set up the number line and we divide it into intervals with our critical numbers as endpoints, this is what we get. We do our test regions, and you can plug in any number you want from any of the regions, and you'll find out, you'll get the sign of the function value. So let's just walk through that. Doesn't hurt to walk through it. Let's say we're looking at this left region here. I want anything in that region. Well, negative 5 is easy enough. Let's plug negative 5 in for x over here where I'm circling with the mouse arrow. I'm going to plug negative 5 in for x. Okay, Negative 5 plus 4 is negative 1. Negative 5 minus 2 is negative 7. Negative 1 times negative 7 is positive 7. And therefore, everything in this region is positive. All right, now let's look at this middle region. Well, the easiest number to test, of course, is the number 0. So let's plug 0 in for x. We plug 0 in for x. 0 plus 4 is 4. 0 minus 2 is negative 2. 4 times negative 2 is negative 8. Therefore, everything in this region is negative. And finally, let's look at this region. 3 should be easy enough. Let's plug 3 in for x. 3 plus 4 is 7. 3 minus 2 is 1. 7 times 1 is positive 7. And therefore, everything in this region on the right is positive. Okay, now in the context of the problem, since this inequality is greater than or equal to 0, then I'm interested in the positive regions. And I'm also interested in the endpoints because the endpoints would yield function values that are 0. And that's okay, since the inequality is a greater than or equal to 0 inequality. Now, before you write the solution to a word problem, you always have to use your common sense. And since it's physically impossible for, x to be negative, then we simply discard this entire left-hand portion of the solution set. And we only retain the right-hand portion of the solution set, which is x is greater than or equal to 2. And therefore, the shorter leg should be at least 2 inches long, since at least is the same as greater than or equal to. Okay, so this was a word problem that uses a nonlinear inequality. And we'll have one of those in this problem set that we're going to do in the next class as well. Classwork, review exercises, part 1. Again, remember that we are now at the end of a chapter, and so right away we begin reviewing for the test. Page 204, numbers 47, 49, and 69, and page 210. Write those numbers down. So in review exercises part 1, there are those 9 problems. And review exercises part 2, we have these 9 problems. Page 208, 13, 17, 21, 33, 51, 53, 81, 91, and 106. So tomorrow, or in our next class, we're going to be working on review exercises part 1, and in the class after that, review exercises part 2, and then the test will follow.